All right, so in this video, I'm going to go over just a quick introduction to simple harmonic motion. And again, just like the other videos, this is not meant to serve as a comprehensive overview of simple harmonic motion, although it's a short unit. What I really want to do here is just introduce some of the main equations, just a little bit of background behind them, and then if you need more depth, AP Live has some great videos and Khan Academy, but this is meant just to get your feet wet. And then some future videos, I'll do some problems to sort of help out. But well, let's just start with the definition of simple harmonic motion. And so simple harmonic motion is defined as some sort of periodic behavior, something that undergoes oscillations that is due to a restoring force that is proportional to the displacement. So let me give you an example. And in fact, we have really two examples of simple harmonic motion. We have the pendulum and the mass on the string. And so in my next video, I'll go over the pendulum a little bit, but let's talk about the mass on a spring. And so if you take this mass, and we're going to say that it's at equilibrium when the position is at 0, and that means that it's not compressed or stretched, it's just static, it's just sitting there. And if we take that spring, or that mass on the spring, and we then pull it to the right or push it to the left, and neglecting friction, neglecting any damping or anything, it's going to oscillate back and forth relative to this origin. And as it oscillates back and forth, we have an equation that describes that. We say that the equation is called Hooke's law, and it's equal to the force is equal to negative K times X, where X is the displacement. And so essentially what it says is if your displacement is positive, your force is going to be negative. Meaning if your displacement is to the right, your force is to the left. And the opposite's true too. If your displacement is to the left, then your force points in the opposite direction to the right. It always causes it to go back towards that equilibrium position. And that's the way it always points. It's the way you want to think about it. Now, if I were to look at this equation right here, I can compare this equation with circular motion. And the reason I say that is because circular motion, so if an object is undergoing some type of circular path like this, where remember we have a centripetal force that points towards the center, what simple harmonic motion really is it's analyzing circular motion, but in one dimension. So another way of saying that is circular motion is simple harmonic motion when it's confined to one dimension. By that I mean, if you don't care about, say, where the object is on the y-axis, you only care about how it changes on the x-axis. You could say as it goes around this circle, it's going to undergo behavior very similar to this mass on a spring. And because of that, we can state, I'm not going to do the full derivation, but we can combine this force with the centripetal force, and we can simplify things down, and we can write the angular velocity or the tangential velocity in terms of the angular velocity. We can do all that, and we can derive an important relation. And what I'm going to do is I'm going to write the important formulas over here on the upper right corner. So the first one is Hooke's law, so that says force is equal to negative kx. The next one, using that derivation, would say that omega is equal to the square root of k over m. If you're curious, how in the heck did I come up with that? You'll see, if you look up online, you'll see a lot of derivations for it. They're calculus based. They're not hard, but they're calculus based, so we're not going to go through it. But the important part is that we can write the angular frequency or angular velocity. Sometimes you'll see it stated either way. So this omega represents the angular frequency and angular velocity as the square root of k over m. And if I also remember, I can write the angular velocity as 2 pi times the frequency f, or usually it's written as 2 pi over the period t. And if that's the case, I can combine these two equations, and I can say that the frequency is equal to 1 over 2 pi times the square root of k over m. And similarly, I can say that the period t is equal to 2 pi over the square root of mass times k. And if you'll notice with these two equations, let me just take the period one. If you'll notice that as the mass increases, the period also increases, which makes sense, right? If you have a very large mass on the end of a spring, then it's going to take longer for it to move back and forth. And so hopefully that makes sense. All right, so what if we want to model this behavior in terms of its position? And so if we want to model in terms of its position, we would say that we have an x, we would say its position is x versus time, here t. And the way you would model it, and again, I invite you to look at those AP Live videos, but essentially when you do model it, the type of graph that you're going to get is going to be a sinusoidal graph. Now, is it sine or cosine? Well, that depends on something called the phase angle. But we're going to keep it simple, and we're going to assume that it starts at time equals 0, and that corresponds to its greatest displacement. So if I were to go back to my, well, I could look at either example, the pendulum or the spring, mass in a spring, but either one, I'm going to assume that you pull it back, and then the instant you release it is when the time starts. And the reason I do that is just because it's a little easier to deal with cosines instead of sines with arguments on them, or sines with phase angles on them. So all that said, we have some cosine graph that kind of looks like this. And this distance right here, so this is going to be my 0 on the x-axis. This distance right here is what we call the amplitude A. The amplitude is just how far you pull that object, or how far that object has been displaced from equilibrium. And so this would correspond to negative A. And we don't learn about waves, but this would be, well, actually I won't even get into that. But what I will say is that we have a displacement A right here, and we can write the equation for our position versus time graph in terms of cosines and sines. And so we can say that the x is a function of t is equal to that constant, what we call the amplitude, times cosine times omega t. And I write omega right here, but this can also be written in terms of 2 pi times the frequency, or 2 pi over the period t times little t the time. But this is the simplest way I know of writing it. And so if we know a little bit of calculus, we can also come up with equations for the velocity as a function of time and the acceleration as a function of time. Now, we don't need to know that, so I'm just going to write them out. But if you are familiar with a little bit of calculus, you can just take the derivative of this once with respect to time, and that'll give you velocity. Take it with respect to time again, that'll give you acceleration. However, I'm just going to write them out. And in fact, I am going to, actually I'll write them right here and then I'll put them off to the side, but I'll write the velocity as a function of time is equal to the negative amplitude times omega times sine theta. And then the acceleration versus time is equal to negative a times omega squared times cosine of omega t. Okay, so actually, since I have a little bit of room, I'm going to write it over here. And so if you think about it, what if we're interested in knowing when the velocity is a maximum and when the acceleration is a maximum? Well, the velocity is a maximum when this function of velocity as a function of time, I should say, when this is equal to its maximum value. When is it equal to its maximum value? Well, it's equal to its maximum value when the argument, or I should say when the sign of this argument is equal to 1. So in other words, when cosine is equal to 1, when sine is equal to 1, those are when you get your maximum values. And so therefore we could say that the velocity max is equal to negative a times omega. And it has to be negative a times omega because our sine needs to equal 1. It can't equal any more than 1, but that's our maximum value. And similarly, we can say that our acceleration max is equal to negative a times omega squared. And I will say that they usually omit these two signs right here just because it's just like momentum, just like a lot of things in physics, we're interested in the magnitude of it, not the direction. And so sometimes you also see these written as each one of these, instead of in terms of omega, in terms of like 2 pi f. That's a little more common to write it like that. So where does this correspond to on our graph? Well, if our velocity maximum is when sine is equal to 1, and our acceleration is when cosine is equal to 1, our velocity maximum occurs right here when our x is equal to 0. And so this point right here, right in the middle, corresponds to your velocity max. And this point right here and this point right here corresponds to when the acceleration is the maximum. So if I were to go back and I were to write my little mass on a spring like this, and this is my equilibrium position, x is equal to 0, and then I take that mass, I pull it over here, and then I release it, the velocity will be a maximum right when this mass passes through the origin, right when x is equal to 0. And kind of counterintuitively, the acceleration is a maximum when the velocity is a minimum. So when the mass on a spring is all the way at its farthest point, it's at its amplitude a, then the acceleration is a maximum and its velocity is a minimum. And the reason for that is because acceleration is all about a change in velocity. And so your acceleration really doesn't have much to do with the magnitude of your velocity or what the velocity is at any instant. It's really equal to the change in your velocity, and that occurs at those endpoints right there as it's oscillating back and forth. And so I think that's about it for this video, but this is the basics of simple harmonic motion, in particular simple harmonic motion with respect to a mass on a spring. And next video I'll go over the mass when it's a pendulum instead of a mass on a spring.